Welcome back to this video tutorial. We can discuss about the design of accumulator register here. So before starting the design part, we need to recollect factors about this accumulator register that we have already discussed in our previous video. Accumulator register is a multifunction register associated with our processing unit, right? So this ALU, that processing unit ALU, can take the content of accumulator register as its input and take content from another some other general purpose register as its B input. After taking this input values, ALU can perform some arithmetic operations or logical operation and finally write the resultant value back into our accumulator register. Okay, so we can list such operations here. This is the addition of content of accumulator register with content of another register B. The resultant value placed back into our accumulator register. This is the case of subtraction. Content of A gets subtracted from the value of register B. Resultant value right back into the same register accumulator. Right? This is the increment operation. This is decrement operation, logical AND operation, OR operation and XOR operation. Okay, so take the content of accumulator as one of the input of ALU and after the ALU operation, write the value back into our accumulator register. So this accumulator is a multifunction register, not like other general purpose register. Accumulator can be used as a multifunction register. Okay, now we need to understand the design of this accumulator register. So this is just a representation of this previous diagram. This accumulator register is associated with ALU always, right? This ALU is actually a combinational circuit. We have already discussed about the design of our ALU, which was a combinational circuit. So that is represented here. Accumulator register is connected with a combinational circuit. That combinational circuit is here our ALU, right? This ALU can take the content of register A, that is the content of accumulator register as one of its input, and take content from another general purpose register, marked it as B here. So after this operation of this combinational circuit, result value placed back into our accumulator register itself. Okay, so this is the block diagram of our accumulator. And for the working of our combinational circuit, here we need various set of control variables. That control variable decide what operation that we want to perform now. Okay. So here it consider the design of an accumulator. We will design this accumulator circuit with 9 different micro operations. So we are going to design an accumulator circuit that perform 9 different micro operations. What are they? First one is A equal to A plus B, addition operation. A equal to 0 is a clear operation, clear the content of accumulator register. Next is A equal to A complement is complement operation. This is logical AND operation, logical OR operation, XOR operation. This one is shift right of content of accumulator register, shift left of content of accumulator register. This one is increment operation over the content of accumulator register, and next one is check for value 0. That means if all the bits of accumulator register is equal to 0, then it set the variable set, the conditional variable or status variable set as 1. All the bit position of our accumulator register is holding currently value 0, then it automatically set our status bit set is set as 1. Okay, for controlling all these 9 operations we need control variables. The control variables are represented here like P1, P2 up to P9. Right, the control variables are used for controlling this micro operations. So this is the function diagram that indicate the 9 different operations that we are going to implement for our accumulator circuit. or we are going to implement such an accumulator circuit that perform all these 9 operations, and these 9 micro operations are controlled with the help of this control variables represented like P1, P2 up to P9. Okay. So first of all, we need to understand some basics information about our JK flip-flop, because we are going to design a circuit with the help of JK flip-flop here. That means going to design an accumulator circuit with the help of JK flip-flop. So this is the block diagram of JK flip-flop. We need J input and K input with clock pulses, right? And the outputs are marked like Q and its complemented form. So this is the truth table representation of our JK flip-flop. If both values are 0, 0, then whatever value present in our Q state which is retained here, that means no change occur to our output state. If J input is 0, K input is 0 and a new clock pulse is provided, then no change occur here in this Q value. That means whatever value present here, it will retain here in the next state also. If J equal to 1, K equal to 1. Next case, if J equal to 1 and K equal to 0, what is the output? The next state of this Q become 1. If J equal to 1 and K equal to 0, after applying a clock pulse, the state of this Q change to 1. Whatever value present here, now its value become 1. Okay. Next is J equal to 0, K equal to 1. J equal to 0, K equal to 1. Set J equal to 0, K equal to 1 and apply a clock pulse. Then change the value of our Q. Whatever value present here, it is replaced with a value 0. If J is set as 0 and K is set as 1, then whatever value present here in this previous case, which is replaced by a new value 0. Next is about 1, 1 case, that is J equal to 1 and K equal to 1. This indicates a toggle case, that is whatever value present here, its complement is available here. While applying a clock pulse, whatever value presented here, the value get complemented now, and the next state indicate the complemented form of previous value. That is the toggle case. Okay, we have already learned this truth table in digital system, right? So our first micro operation is an addition. Add content of register B with accumulator register content, and the result is placed back into accumulator register. This particular add micro operation is controlled with the help of a control variable P1, right, which is represented in our function table. Add micro operation is initiated with control variable P1 value become 1. If P1 equal to 1, then the accumulator circuit perform this addition operation, or the accumulator content is passed to our ALU and also take some content from some other general purpose register and perform addition operation. For supporting such an operation, we need to consider a design an accumulator circuit. Okay, for performing such an addition operation, this part of accumulator can use a parallel adder composed of full adders. We have already discussed about this in our ALU design part. In order to perform addition operation in ALU, we considered there a parallel adder circuit with n number of flip-flops. The same concept is used here also for the design of accumulator. In order to perform this addition operation, we need to consider parallel adder circuit with full adders. Okay, so this is the case. We need to perform addition. We need to add the content of A with accumulator with content of some other general purpose register represented as B here, and also consider the carry in values. And after this addition, we need to write the resultant value back into A register itself. That is the property. So while using accumulator register in case of addition micro operation, after the addition we need to write the resultant value back into a register itself. Okay, so this is the case. Consider the present state of A is 0, present state of B is 0. This AI, BI, CI, etc. actually indicate one bit of our entire register. Okay, so the circuit for a single stage is available or generated, then same can be repeated for other stages also. So this AI, BI, CI, etc. indicate a single state or a single bit of our register. Okay, so this first case, present state of AI is taken as 0, BI as 0 and CI with 0. So after the addition operation 0 plus 0 plus 0, the new state, the resultant value placed back into our accumulator register. That is, we are going to perform A equal to A plus B. After addition, A plus B, and also we need to add the carry in value. That is A equal to A plus B plus C in. Right? A equal to A plus B plus C in. After addition, resultant value placed back into our accumulator itself. So 0 plus 0 plus 0 is 0 itself with carry out equal to 0. Right? And for the next case, suppose AI with 0, BI with 0 and CI equal to 1. What is the result of this addition? 0 plus 0 plus 1 means AI become, new state of AI become 1 with carry out equal to 0. Next state, 0 plus 1 plus 0. Then AI become 1, carry out become 0. Again 0 plus 1 plus 1. Next state of AI is 1 plus 1 means 0 with carry 1. Carry out become 1. Right. Next is 1 plus 0 plus 0. That is, next state of AI is 1 with carry out equal to 0. Again 1 plus 0 plus 1. AI become 1 plus 0 is 1. Again that 1 plus 1 is 0 carry 1. Okay, 1 plus 1 plus 0 is 0 carry 1. 1 plus 1 plus 1, that means new value of AI is 1 with carry out equal to 1. Okay, so from the present state of AI and with new input BI and carry in value, now generate the next state of AI and C out values here. Right. So based on this, we need to identify what are the J and K value required for our JK flip-flop implementation. For this present state of AI is available, next state of AI is available, generated here, right? With the respect to this present state, now generated or obtained the next state of AI. So based on this, we need to identify the proper input combination for J and K for our JK flip-flop. For generating that JK input combination, we need to consider the excitation table of our JK flip-flop. Okay, so the excitation table is here. If the present state value of is 0 and the next state value is again 0, then what are the combination for J and K input? 0 and don't care. Right? And present state is 0, next state is 1, then the J and K input is 1, don't care. And present state 1, next state 0, and the J input may be anything, that is why this don't care, and but the K input must be 1. And present state is 1, next state is 1, the J input may be anything, that is why this don't care here, and K must be 0. So based on this excitation table or based on this information, now we can decide the J and K input values. If the present state is 0 and the next state is 0, this particular combination, the J and K input may be 0 and don't care. Don't care means 0 or 1. Whatever it may be, it doesn't affect the transition from present state to next state, right? Next is present state is 0, next state is 1. Present state is 0, next state is 1. then the J and K input must be 1 and don't care. 1, don't care. Right? Present state 0, next state 1. Then present state 0, next state 1. The same pattern, 1, don't care. 1, don't care. Present state 0, next state 0. 0, 0 means 0, don't care. 1, 1. 1, 1 means don't care, 0. Again 1, 0. 1, 0 means don't care, 1. Okay, so like this we need to identify where is J and K value possible for implementing this particular addition. So using this J and K values, we need to derive Boolean function representation corresponding to J, K and this Cout representation. So while considering this J column values, now we can simplify this K map and generate an expression for a Boolean function for this J input as bi ci complement plus bi complement ci. Right? While simplifying this, but get this one is AI, this is BICI, right? BICI. So while considering this particular case, this is BICY complement and this one is BI complement CI. Okay, this one is BICI complement and this one is BI complement CI. Okay, and similarly here after simplifying this, the configuration is this one is AI and this is BICI. Column wise AI and this one is BICI. So while simplifying this, we get an expression BICI complement plus BI complement CI. And for this Cout expression also, by simplifying we get AI BI plus AI CI plus BI CI. Okay, so these are the Boolean functions obtained after simplifying this J, K and Cout representation. Now we need to consider our control variable along with this Boolean function. So this J input of our accumulator, this AI actually indicate a particular stage of or particular bit of our accumulator, A0, A1, A2 up to AN, etc. Right? So we need to consider our control variable also along with each of this expression. That is why JAI expression become BICI complement PI plus BI complement and CI and PI. Sorry, P1. Okay, we need to control or we need to attach the control variable with each and every expression. K input become BICI complement P1 plus BI complement CI P1. And also with this carry out expression, here we need to this is the output of a JK flip-flop. This carry out. Here we don't want to consider our control variable. The control variables are always connected with J and K input. We don't want to consider the control variable with the output from the JK flip-flop. Okay, this is actually expression for Cout. Right? So we don't want to consider the control variable along with this expression. But we want to consider this control variable P1 with these expression associated with J and K input, because they are representation or Boolean function for J and K input of our JK flip-flop. Okay, so like this we can consider the second function, clear function. Okay, in order to perform clear function, we need to consider another control variable P2. Okay, from this truth table of JK flip-flop, in order to clear, that means make the value of Q in the next state, we need to make the value, whatever value present here in the current state, we need to make it as 0. In order to get the 0 in the next state, what are the j and k input requirement? J must be 0 and k must be 1. Okay, so we need to consider the control variable p2 along with our j and k input. So 0 into p2 is actually 0 itself. 1 into p2 is p2. Into means AND operation, right? 0 and p2 is 0 itself. 1 and p2 is p2 itself. So this is the expression or the Boolean function required for performing this clear operation with the help of control variable p2. Okay. So next case is the complement operation with the help of the control variable p3 to register A. Okay, so consider this. When from this truth table, it is clear that when j value become 1 and k value become 1, whatever value present in our q state, the next state generate its complemented form. That is the toggling of our state values. So for getting the complemented form in the next state, we need to apply j equal to 1 and k equal to 1. So along with this j and k input, here we need to consider the control variable p3. That 1 and p3 is p3 itself. 1 and p3 is p3. Right? So this is the expression or the Boolean function corresponding to complement operation. So next is about logical AND operation. This operation is controlled with the help of a control variable p4. So for generating the Boolean function for this particular expression, we need to consider again this excitation table, and the present state is 0, 0, A with 0 and B with zeros, and the possibilities are 0, 0, 0, 1, 1, 0, 1, 1. So while performing AND operation with this present input, what will be the next state value of our A accumulator bit? If it is 0, 0, while performing AND operation between these two, the next state becomes 0 itself. And 0 and 1 is 0 again. 1 and 0 is 0, and with 1 and 1 it is 1. Okay, now we need to consider this j and k value in order to generate this particular next state values corresponding to this given present state values. Okay, for that we need to consider this excitation table for our jk flip-flop. Okay, consider the present state of ai is 0 and the next state is 0. In order to get this 0, 0, the jk combination must be 0, don't care from this particular table. This 0, present state is 0, next state is again 0, the same combination for j and k, that is 0, don't care. Right, next is 1, 0, then 1, 0 means the jk combination must be don't care 1, and with 1, 1 the jk combination must be don't care 0. So using this j and k values, now we can perform this K-map simplification, and while performing the K-map simplification for this j input, we get a Boolean function like ja equal to 0, and for this ka equal to, this is bi complement. So while considering this control variable p4 along with this j and k input, now the expression become, or the Boolean function corresponding to this particular logical AND operation become jai equal to 0 and kai equal to bi complement p4. Okay, and similarly for our logical OR operation, which is controlled by the control variable p5. So the same procedure repeated here, right, with the help of this jk flip-flop excitation table. The excitation table for this jk flip-flop generate various j and k input combination, then performing this K-map simplification. Now we get an expression j input must be of bi and k input of value 0, just the reverse of our sorry, not the exact complement, Here in case of logical AND operation, the expression is like JAI equal to 0 and KAI equal to BI complement P4. So here, after the simplification and while considering this control variable also with this input representation, now this JAI become BI P5 and K become 0. 0 and P5 is 0 itself. Okay, so the next case is XOR representation, and this XOR operation is controlled by this control variable P6. So again we need to consider this present state of A with next state. In case of XOR operation, when this XOR operation generate value 1, if either of this A or B become 1, then this next state become 1. So if it is 0, 0, next state of AI is 0. After XOR operation, result is 0 itself. And for 0, 1, the next state is 1. 1, 0, the next state is 1. And for 1, 1, the next state is 0. So consider this present state values and next state values. And consider this excitation table. Identify corresponding JK combinations. And then simplify for this J and K separately and identify this expression. Both are BI, right? Both are BI here. So consider this control variable also along with this Boolean expression. So this JI become BI P6, BI and P6. K become BI and P6. Same expression. The next is about the shift right operation, which is controlled by the control variable P7. Shift right operation means shift one position to the right of content present in accumulator register. Suppose accumulator register is of size 4. The positions are represented like A1, A2, A3, A4. So after this shifting operation, the content in after the shifting operation, that means in the next state, the first position hold the value from A2 of our previous state. Okay. Second position in the new state hold the value from third position of our previous state. And the third position in the next state hold value from the fourth position from our previous state. And the vacant position in the MSB bit position is filled from an external serial input. Okay, so for performing this particular operation, the Boolean functions are given like this: JAI equal to AI plus 1 and P7, control variable P7, and KAI equal to AI plus 1 complement and P7. Okay, from this it is clear that after shifting to right one bit, each position is filled from one position back in its previous state. A2 or this first position in the next state is holding value from the second position in the previous state. So that is by this expression. But this K input is set as a complemented form of AI plus 1 and P7. How it does represent? What is the reason of setting this complemented form here? For that, consider this one example. Suppose the AI plus 1th state now holding the value 0. So the J input is assigned with this 0. 0 into P7 is 0 itself. And the K input is complemented form of AI plus 1th value. That is 0 complement is 1. 1 and P7 is P7. Okay, so whenever this P7 value become 1, it shift right operation occurs. So now the J value equal to 0 and K value equal to 1 and P7. In order to perform this shift right operation, P7 must be equal to 1. So this 1 and 1 is 1 itself. So the case is J input is 0 and K input is 1. J input is 0 and K input is 1. The expected next state value is 0. So the AI plus 1th position previously holding the value 0, which is shifted to AIth position, right? So that is why this complemented form assigned here in this K input, okay, which is derived from this truth table. One more example. Suppose the I plus 1th position now. In the previous state, the I plus 1th position hold the value 1. So this expression JAI is 1 and P7, and KI is complement of this state value, that is 1 complement is 0. 0 and P7 is 0 itself. Okay, and this shift operation with this particular input, and this shift operation takes place only when P7 value equal to 1. So 1 and 1 is 1 itself. So now J value is 1, K value is 0. From this truth table, J value is 1, K value is 0. Next state hold the value 1. That is the same value 1 available in AI plus 1th position, which is shifted to AIth position after performing this shift right operation. So the corresponding Boolean function is like this. Okay. So the next case is exactly the reverse of the previous shift right. Now it is shift left. Shift one position to the left, and the vacant position in the LSB bit is filled by an external serial input value. And this operation is controlled by the control variable P8 here. So here expression is like this. JAI equal to AI minus 1 and P8, KAI equal to AI minus 1 complement at P8. That means each position after shifting, each position is filled from one position to the right. AIth position is filled from AI minus 1th position in the previous state. That is why this expression. And here also the K value is represented with the complemented form of AI minus 1th position value in the previous state. So consider this example. Suppose our AI minus 1 value hold 0. Okay, so using this expression, this JAI become 0 and P8, that is 0 itself. And this KAI become its complement, that is complement of AI minus 1, that is 1 and P8, that is P8. And this operation takes place only when this P8 value become 1. Then this 1 and 1 become 1 itself. So now the J value equal to 0 and K input become 1. 0, 1 is 0 itself. So after setting the J input as 0 and K input as 1, and by enabling this control variable P8, the next state here we have the value 0. That is the value present in the AI minus 1th position before shifting. Right? This is available here in AI now after this shift left operation. So the corresponding Boolean function is thus. Okay. Next is about the increment operation. This increment operation means we can increment the content of A register by 1. This operation is controlled by a control variable P9. So for performing this increment operation, the register must behave like a synchronous binary counter with this P9 as the control variable. Okay, so for understanding this working of our synchronous binary counter, consider one example. Suppose A is of length 4, that is accumulator register is with 4-bit capacity. The bit positions are represented like this: A1, A2, A3 and A4. And initially this position with value 0, 0, 1, 1 respectively. If it is 0, 0, 1, 1, after this increment operation, the next count will be 0 1 0 0. This is decimal 3. This is the binary equivalent of decimal 3. After increment operation, its value become 4. This is the binary equivalent of decimal 4. Okay, in order to design such a circuit, we need to follow one principle, that is the A1th position value is always get complemented. Whatever value present in A1th position, it is always get complemented. Then A2. A2 is complemented if A1, the previous state of A1 is 1. If the previous state of A1 was 1, then in the next state A2 value get complemented. And similarly for A3, in the next state the A3 value get complemented if in the previous state A2 A1 value or the combination A2 A1 contains full of ones. And also the A4 is get complemented in the next state. In the next state A4 get complemented only if in the previous state A3 A2 A1 contains full of 1. Once more, A1 value always get complemented, and A2 in the next state get complemented only in the previous state A1 is with value 1. Okay, similarly A3 in the next state get complemented only if in the previous state A2 A1 contained 2 full 1. And similarly if A4 state of next state, A4 of next state contain a complemented value only if A3 A2 A1 in the previous state contain full of ones. So consider this example. This is the present state 0 0 1 1. Okay, so by following this principle, we need to complement this LSB bit always. Whatever value present here, we need to complement it first. Then for this A2, the A2 value need to complement only if in the present state or in this state, this is the next state and this is the present state. In the present state, this A1 contain value 1, then we need to complement this A2 in the next state. Here it is 1, and in here the present state A1 is with value 1. So here we need to complement. So here it is 1, so its complemented value is 0. And for this A3, in order to generate the next value for A3, now we need to consider the present state of A2 A1 combination. Here it is both A2 and A1 are 1. So we need to complement A3. Okay, and in the next state we need to generate a value for this A4th position. Okay, for that we need to check whether this A3 A2 A1 value in the present state is full 1. Here it is not. A3 is 0 but A2 A1 1, but all three is not 1. So we don't want to complement here. Simply transfer the value to the next state. So the next state value is 0 1 0 0. Okay, so this is the principle of a synchronous binary up counter. Okay, so this is the diagram or the circuit of a 3-bit synchronous binary up counter. And a synchronous counter and is implemented with the JK flip-flop, the lowest order position is always complemented with every clock pulse. Okay, so in order to get the complemented form, we need to input the J and K input as, or we need to set the J and K input as 1 1. Okay, so we must maintain this J and K input of our first state or the LSB state as 1 always, because at every clock pulse this state get complemented. The output of this particular LSB state always get complemented. That means the toggle state. In order to get that, we need to set this j and k input value as 1, 1. Okay, and based on that, the current or the present q value and the control variable decides the next or derive this E2 value. This E2 value decide whether to complement or not the next state value A2 here. Okay, and this present state A2 value and the control variable decide or generate an E3 value. This E3 value decide whether to complement or not the A3 value. Okay, the present state A3 value and the control variable decides this next bit of our shift operation. Okay, so for that consider this. This is the 3-bit information. Okay, A1, A2, A3 with value 1, 1, 0 here. Okay, so first of all, this j and k value is 1. So we need to complement this A1 to position value always. In the next state, this A1 value always get complemented. Okay, so now consider this value. This is 1 here. In the present state, A1 value is 1. That 1 value is logically AND with the control variable P9 which generate E2. This E2 decide whether to complement this A2. Okay, so in order to generate a value for A2 in the next state, we need to consider the present value of our A1. It is 1 here. If it is 1, we need to complement the current value of A2. That complemented value is transferred to next state of A2. So here it is 1 now. So this 0 is transferred. Its complemented form is transferred to next state. Okay. And this next state A3. Suppose this current state of A3 is 0. Okay. Now we want to check whether in the next state this A3 hold 0 or 1. For deciding that, we need to check the present value of A2 and A1, which is obtained from this AND gate output. That is, this E3 actually indicate the value of this A1 and A2. If both this present state value of A1, A2 both are 1, then this E3 become also 1. Okay, if this E3 is 1, then we need to complement this A3. If E3 is not 1, then we don't want to complement E3. We can directly transfer the current value of A3 to the next state. Okay, but here the present state value of A1 is 1 and present state value of A2 is again 1. Okay, this A1 value is entered with our control variable P9. In order to perform this increment operation, the P9 value must hold the value 1. So the 1 and this A1 value 1 generate an AND operation result E2 as 1. That E2 value equal to 1 is ANDed again with this A2 value. The present state A2 value is 1. That 1 is ANDed with this A2 value. E2 is equal to 1 now. 1 and 1 is 1 again. So this AND gate generate an output value 1 here. That is E3 equal to 1 now. This E3 decide whether to complement this A3 or not. Now this E3 equal to 1. That 1 is applied here in J and K. If both J and K equal to 1, then it perform a toggle operation. Toggling means it complement the current value. So A3 is now 0. So it complemented and it set 1 in the next state for A3. Okay. So now here we need to eliminate one value, right? So that is represented here by this if. This is not the elimination. Sometimes here it represents a carry out value after increment operation. That carry out value is represented by this E4. Okay, this E4 is indicated by this AND operation between A1, A2, A3. If all are 1, then E4 become 1. Okay, if any of this value, here in this case the present state value of A3 is 0 and this E3 is 1. 1 and 0 is 0. So E4 indicates 0. That means after this increment operation, here it generate no carry out value. The carry out value is 0 here. Okay. Now consider another example with A3, A2, A1 with value 1, 1, 0. Okay. So first case, J and K is directly applied with input value 1, 1. So directly complement this A1 value. Here it is 0. So in the next state A1 hold the value 1. The complemented form of current state value. After that, this AND gate generate 0 and 1. That is E2 is 0. E2 is 0, then 0, 0. 0, 0 means we don't want to perform any complement operation. Directly transfer this A2 to the next state. So this A1, A2 value is directly transferred to the next state. Okay, again this A2 is present state of A2 is 1 with E2 is 0. So E3 again is 0. This 0 is applied to this J and K input of this third state JK flip-flop. So here it is 0, 0 from the truth table. If J and K both are 0, we don't want to perform any complement operation. Directly transfer this current value of A3 to the next state. So here this A3 is with current value 1. So which is directly transferred to the next state. Okay. So again this current value of A3 is 1 and E3 is 0. 0 and 1 is 0. So after this increment operation, here it does not generate any carry out. The carry out value after this increment operation is again 0 here. So this is the circuit diagram for a 3-bit synchronous counter. This type of synchronous counter is used for implementing an increment operation over accumulator register content. Okay. So the expression is like this. JAI and KAI is implemented with this A values. Okay. So this A value is obtained as a result of AND operation between previous E value and present state of AI. EI plus 1 means previous E value and present state of AI. Okay, and this E1 is actually indicate this EI is actually indicate this control variable P9 itself. Okay, in order to perform this increment operation, P9 become 1, which is directly connected to the first JK flip-flop input. Okay, so this J and K become 1 and the present value of A1 is ANDed with this E1 value and generate E2. This E2 decide the next state for A2 and present value of A2 and this E2 value ANDed and generate E3. This E3 decide whether to perform, whether to transfer or complement the A3 value in the next state. Okay, and similarly this A3 present state of A3 and our E3 value generate value for E4, that is the carry out value after increment operation. Okay, so this is the general expression. First state J and A is connected with E value. E value is actually 1 1 in the first flip flop. In all other cases, the AND gate result of previous E value and present state of AI value. Decide next J and K values in all other cases other than our LSB JK flip-flop. Okay, so keep this expression in your mind. Next is about check for 0. Okay, variable set is an output from the accumulator used to indicate a 0 content in register A. Check for 0 means if all the bit position of accumulator register is holding value 0, then we can set a variable set as 1. Set is a status bit, status register bit. This status register bit set, this set is a status register bit. That particular bit is set as value 1 if all the bit of accumulator register currently holding the value 0. If all the bits of accumulator register currently holding the value 0, then we can set Z as 1. Otherwise, this status bit Z holding the value 0. Okay, so consider this diagram. If all the bit position of our accumulator register is holding currently value 0, then its Q complement value become 1. If Q is 0, then Q complement is 1. So, we need to consider this Q complement part here. This part is added with this control variable value Z. Z is initially set with value 1. Okay, so that Z value and this Q complement value get added here. Logically AND operation is performed here and generate Z2 for the next state. Okay, if this Q complement value equal to 1 and Z1 equal to 1, this Z2 become 1. If Q complement equal to 1 means the present state of this A1th position of our accumulator is currently holding value 0. That is why this Q complement become 1. That 1 is ANDed with this control variable value 1. So Z2 become 1. Okay, this Z2 is get ANDed with this Q complement of our A2 state. If A2 again holding value 0, then this Q complement become 1. That 1 is again ANDed with this Z2 value. Z2 is already 1. If this 1 and this Q complement value 1 is ANDed again and generate Z3. If this state suppose holding the value 0, then Q complement become 1. That 1 value is ANDed with the previous value of Z2. Okay, so this 1 and 1 become 1 here. That form the value of this Z3. Okay, that Z3 is ANDed with Q complement value of our state A3. Suppose A3 is also holding the value 0. That means Q equal to 0 here in the present state. Then this Q complement value, that is 1. That 1 is ANDed here and generate an output value Z4. That Z4 value is actually used for setting the status register bit Z. That indicate whether the register is completely holding value 0 or not. If all the bit position of our accumulator register is currently holding value 0, then our status register bit Z holding value 1, or status register bit Z is set as value 1, which is derived with the help of this circuit. Okay, so the expression is like this. This next state set value, that is set I plus 1, is equal to current set value and complemented form of our present state. If it is 0, then Q complement is 1. Okay, the complemented form of current state is ANDed with the previous set value set I, that generate the next state set I plus 1th value. And initially this Z is set with, or this Z1 is set with value 1. And the final set4 value here, which is used for setting or resetting the status bit is set. That is set n plus 1 is equal to set. Okay. So all these are the 9 different operations that are going to perform using our accumulator register with various control variable P1 to P2 up to P9. Okay. So all these are the expression that we have already derived here. Okay. So all these are the expressions. Now we need to collect together all JA expressions and KA expressions. This C output, E output and Z output. Okay. So after collecting all these terms together, J terms together, K terms together and C terms and C, E and Z terms separately. Okay. So after collecting terms separately, this Ji term become like this. So the Boolean function for a typical accumulated stage is like this. The J input must be like this. And the K input of this particular stage must be like this. Okay. And the carry out from each of the stage. What are the carry out? C out and this E output. This is actually used in case of increment operation or the carry out generated in the increment operation. And this set output actually used in case of condition checking. So these are the 3 carry out values from each of the stages. Okay, and this is the Boolean function corresponding to C carry out, E and Z carry out. And this is the Boolean function representation corresponding to J and K input. Okay, so using these expressions, now we can consider the combinational circuit like this. Okay, so in the previous expression, this set output is like the previous Zi value and Ai complement. Okay, so Zi plus 1 is the AND operation between previous Zi value and the complement form of current state, that is Q complement and Zi, that generate the next state Zi plus 1 value. Okay, and similarly this Ai plus 1 output, the expression is like this, Ei and Ai. Okay, so this Ei plus 1 is a result obtained from this AND operation between this Ei and Q output of our present Ai state, that is Q and Ei. Decide Ei plus 1th output. Next is Ci plus 1. How to obtain this Ci plus 1 or the carry out value to the next state? This is actually Ai Bi plus Ai Ci plus Bi Ci. That is Ai Bi, or next is Ai Ci, or the third term is Bi Ci. So these 3 ANDed terms add together and generate the next carry out value, that is Ci plus 1th term. Now we need to set the J and K input of our current stage of accumulator. J expression is a lengthy term. The expression is like this, J expression and the K expression. Okay, so based on that, J input is actually Bi Ci complement P1. Okay, so this term. The first term is BI CI complement B1 B1 BI and CI complement. This one form one of the term for this OR gate. Next is BI complement CI PI. BI complement CI PI. Okay. Third term is P3 itself. P3 directly given as an input to this OR gate. Next one is BI P5. BI P5. Where is this P5? This is P5 and P5. Sorry, BI P5. This is given to this OR gate. Next term is BI P6. This is for shift operation. This BI P6. So BI P6 given to this. Next is AI plus 1 P7. AI plus 1, sorry, this two, BI P5 and BI P6 related to logical operation. Next one is for shifting operation, AI plus 1 and P7. Okay, here it is, AI plus 1 and P7, which is given to this OR gate. Next is AI minus 1 P5. AI minus 1 P5, which is again given to this OR gate. Next is EI itself. So this all terms are ORed together, and that OR gate output decide this J input of our current accumulator stage, and similarly for this K input also. Okay, so this entire diagram is derived from this Boolean functions. This expressions for J and K input of our current state, and these three expression for carry output from the current state. Okay, so next is about the 4-bit accumulator constructed with 4 stages. Okay, an accumulator with 4 stages. Okay, and these 4 stages are represented like this here. And what are the input required here? This B1, B2, B3, B4 actually indicate the different bit positions. Okay, and from our previous discussion, in order to perform our condition checking, the first set input must be always 1. That is why this LSB state, which is directly given value set 1. Then the current state complement value and the set 1 value decide this set 2 input of our next state. The complemented state of this stage and the set 2 input decide set 3 input of our next stage. The complemented form of this present state and the set 3 input decide set 4 input of our next stage, and so on. Finally, this set 5 stage decide whether to set this set bit of our status register as 1 or 0. Okay, next, for performing our addition operation, first carry flag value. The carry flag value from the status register is directly given as an input to the first stage. And after this addition operation, the carry out value, that is C2, which is passed to the next carry input value of our next stage. And after the addition of our second bit, the carry out value, that is C3, is passed to next state as a carry input value. And after addition from here, the value, carry value generated here, which is transferred to the next state. And finally generate a carry output value, which is transferred to the carry flag of our or carry bit of our status register. Okay, this particular serial input is given to our A0 in case of our left shift operation. In case of left shift operation, a vacant space obtained in the LSB bit, which is filled by a serial input from external. So that input is given here to this last stage, this first stage directly. Okay, and the stage of this particular first stage of our accumulator decide what value comes in next stage. That is, the present state of A1 form the next state A2 value, and present state of A2 form the next state A3 value. The present state of A3 form next state of A4 value, and so on. And this last value of A4 is eliminated. Okay, and similarly for shift right operation. Okay, shift right operation, an external input is given to our vacant position generated in the MSB bit position, that is here in this A file. So after shifting, the A4 value is filled from the previous state value of this A5, right? A4 is set as previous value of this stage. This fourth stage value set as the next stage value of A3 in case of right shift, and this present state A3 value available here in this A2 position after right shift, and this A2 value, present A2 value available in A1 position after right shift. So an external serial input is given to this position, because after right shift a vacant position is generated in the MSB bit, which is filled by a serial input value. Okay, and for this increment operation, we need to provide a control variable, that is P9 equal to 1, which is directly provided to the LSB stage, because both J and K value need to be 1 in order to perform complement operation in every clock pulse. That complement operation always takes place in case of this last stage. Okay, in case of our increment operation. So this P9 control variable is directly given to our first stage. So based on this value, this E1 and present state of our A1 decide this E2. That E2 decide what value comes in A2 state after increment operation. So the present state of A2 and this E2 decide what value comes in this A3 state in the next state after increment operation, and so on. Okay, and finally this E5 indicate a carry value after the increment operation. Okay, so in case of increment operation, this control variable is given only to the first state. For all other 8 micro operations that is listed in the previous function table, all other operation, we need to supply this control variable to all the stages. But in case of increment operation, this control variable is connected with only the first stage. Okay, and this E2, E3, etc. are deciding the next stage, or controlling the next stage increment operation. And for other operations like increment operation, logical operations, condition checking, shifting operation and everything, this control variables are given, that is P1 to P8. All other control variables are connected to all the 4 stages directly. And also we need to provide this clock pulse to each of the stages. Okay. So this is a university question. The question was for designing a 4-bit accumulator with 4 different stages that perform 9 different micro operations listed in our previous function table. Okay.